Okay, what we're going to work on is inequalities. That's what most of life is, okay, as we were just talking about. Now, how do you do this with quadratics? Well, what's going on here as far as the approach to the course is we started out with linear functions, which are fairly easy to work with. We boosted it up a little bit to quadratics, which have an x squared. And then as we move into chapter 4, we're going to get into x cubes, x to the 4th, x to the 5th, then x to whatever power you want. Okay? So we're just kind of moving things on up as we move forward. All right, so what do we after here? Understand how to basically go after quadratic inequalities. What is a quadratic inequality anyway? That's something like 3x squared minus 4x plus 8 has to be greater than or equal to 10. So it's some kind of a situation where it doesn't have to equal a specific number, but it has to be at least so much or no more than something or other. We're going to look at how you solve them with graphs as well as tables. And we're going to look at how do you solve them just like this. Realistically, most of the time it's going to be symbolically. You're going to have to remember how to do the factoring and all that good stuff. Okay. Remember, if you have, wow, there are 4 different signs that you can use. If it's not an equal sign, but if it's one of these 4, we're good to go. It's an inequality. How do you go about solving these things? Let's go after some of them. Okay. How would you solve the first one there? Yeah, the first one, part A. Yeah. Yeah. What we wind up doing, yeah, that was a good question. Wait a minute, if it's an inequality or an equality, does it still have to equal 0? What we're going to do in every case is we're always going to go back to, let's make it equal 0 because that's easy enough to work with. With it equaling 0, if you take a look down here, you can factor it into 2 pieces. And the nice thing about it equaling 0 is that means one of the 2 pieces has to be 0, doesn't it? Because if you multiply 2 numbers together and it equals 0, one of those 2 numbers has to be 0. Which is what allows us to go from right here to say, well, gosh, it might be the case that 2x plus 1 is 0, or it might be the case that x minus 2 is 0. That's what allows you to set each of those equal to 0. Is one of them has to be 0. So this then gives you x is a negative 1/2 and x equals 2. Okay, where do we go from here? Well, what we can do is we can draw a line, set up our negative 1/2 and our 2. Where do we get these numbers? Where did negative 1/2 and 2 come from? Yeah, there are solutions, aren't they? Those are where it equals 0. What you can do then is, you see how we have this factored? We have this 2x plus 1 times the x minus 2. Okay. At negative 1/2 and at 2, it equals 0. Well, just for grins, let's pick a number over here. Would be an easy number over on that left interval to work with. Negative 1. Okay, that's a good choice. And what we're going to do is we're just going to take 2 times the negative 1 plus 1 times negative 1 minus 2. Now, you don't have to get fancy on this. In this first term, you have a negative 2 plus 1. Is that going to be positive or negative? negative 2 plus 1 is negative. Yeah, it's a negative 1. Negative 1 minus 2, that's going to be negative. Yeah, it'll be a negative 3. When you multiply a negative times a negative, what do you get? Positive. What that tells us is the numbers over in this interval are going to return a positive value. Moving over to the next interval. What's an easy number in that middle interval to work with? How about 0? Is that pretty easy? Do you see it's in there? So what we would do is 2 times 0 plus 1, 0 minus 2. This first term here is going to be 0 plus 1, well that's positive. 0 minus 2, that's negative. When you have a positive times a negative, the results are negative. So that means any value that we pick in this center interval is going to give us a negative. Yeah, we're headed to the right side now. What number would work if we were to pick something out on the right side? What number could we use there? I know there's an infinite number of choices. How's 3 sound? Okay. So what we can do is we can take 2 times this 3 plus 1 times 3 minus 2. Now on the first part, don't worry about what the number is. Is it positive or negative? It's going to be positive, isn't it? The second number is going to be positive. So that tells you that this whole section over here is positive. Now that may feel kind of weird. Not worried about an exact value, just is it positive or negative. But that's okay. That's all the more information you need. Because it then allows you to go shopping. If we want less than 0, that means it's going to be a negative interval, isn't it? The answers to part B are going to be in that middle interval. Now notice it's strictly less than 0, so that means it's going to be a negative 1/2, comma 2 with parentheses, not brackets. If we want positive, well gosh, we got a couple of places we can go shopping for positive. There or there. That's going to give us negative infinity all the way over to negative 1/2, and we're going to use a parentheses because it's not greater than or equal to. And along with that, unioned with, we can go from 2 to infinity. Does that make sense how to solve that? And these inequalities are just that straightforward to solve. That's all there is to it. Yes, sir? Ah, yeah. If it's equal to, it's going to be this point right here and that point right there. X equals a negative 1/2 or 2. Yeah. When you're solving these inequalities with quadratics, all you got to do is get it factored, graph the solutions on a number line, and then check numbers in each of the intervals that you have. Is it possible that you'll choose different numbers than somebody else to check the intervals? Yep. But you'll get the same numbers. You'll get the same values back. The same section's positive, the same section's negative, and it doesn't matter. Okay? If you take a look at this, okay, notice here the graph gives us x is 0, or x gives us an intercept. The y value is 0, right? Because if we take this 2x squared minus 3x minus 2 and set it equal to 0, this whole left-hand side is just another way of saying y equals 0. There are two places where y is 0. One of them, bless you, is when x is a negative 1/2, and the other one is when x is a positive 2. If you take a look at this, notice the leading coefficient's positive. So that means it's going to be a parabola. It's going to open up. Now that we know these two solutions, we can list them as places where the graph is going to intersect the x-axis. So you've got a couple of points there. Does that make sense? We know it opens up. Now, here's something kind of cool. We can also figure out where this is. Because this is halfway between x equals negative a half and x equals 2. Well, if it's halfway in between, how do you find halfway between two numbers? You add them and divide by 2. So to find the x value that's halfway between, we would take the negative 1/2 plus the 2 and divide the whole thing by 2. Oh, we're just doing an average, aren't we? Yeah, that's all you're doing there is an average. So this is going to give you 1.5, or 3/2, divided by 2. Did you know 2 is a fraction? It's really 2 over 1. Uh-oh, when you have a fraction over a fraction, how do you do the work for that? You invert and multiply, don't you? So this would give us 3 over 2 times the 2 over 1 inverted is going to give us 1 over 2, which will give us 3 over 4. So the x value that is halfway between is going to be at 3/4. Right about there. Now that you have the x value, is it possible to get the y value? Yeah, how would you get the y value? You plug it back into your original function, and that'll give you the y value for that particular x value. Does that make sense to everybody? Okay. So the cool thing is, when you know your intercepts, you can always figure out where the vertex is going to be. It's going to be halfway between them. So all you got to do is add the two together, divide by 2, and boom, you're good. Does that make sense? Everybody good? All right. Another thing we can do here is suppose we want to know, oops, what happened to the slide? Suppose we want to know where is this 2x squared minus 3x minus 2 greater than 0. Now remember, that equation is the y value, isn't it? So what we're asking now is where is the y value greater than 0? Where is it above the x-axis? Well, the way you can figure that out is you look at your graph, and it's above the x-axis over in this area. It's above the x-axis over in this area. So what we're going to do is we're going to start at this point right here, go that way, start at this point right here, and go that way. Does that make sense what I'm doing? Is everybody okay? So this is going to give us the interval from, oh look, right there it is. Negative infinity to a negative a half, along with 2 to infinity, are the places where the graph is above the x-axis. Are you okay? Another way to do this, and this is not the prettiest way, I would not encourage you to do things this way unless you're really desperate. I would be much more inclined to do it with a graph. Okay. Another way to do this is with a graphing calculator that has a table, okay, like a TI-83 or 84. You can plug in values and see, is the y value that comes out positive? Oh, it's 0. Oh, here it's negative, negative. Here it's 0. So anything from this value here over to this value here, in the middle part, it's going to be negative. Well, that's our negative 1/2 to positive 2 that we had gotten earlier, somewhere up here. Here we go. Okay, remember, if it's less than 0, it's this negative 1/2 to positive 2. It's another way to get the same thing. Personally, I am not comfortable using those table functions. One of the problems with the table functions can be, what if your root is 0.666666666666? Where's that going to be on the table? It's not. Okay. So you got to be careful. There's some things that you got to fiddle with if you're going to do this with the table display. Okay. So let's see here. We got an equation. And what this is dealing with is being able to decelerate in time and be able to keep the car between the yellow and the white line on a curve. And the question is, what would be a safe speed limit for this? At about 200, okay, the car comes off the track. Okay, here let's go forward a little bit. Okay. Okay, so let's see what's going on. The road ahead for only 200 feet. You can, oh man, you can only see the road ahead for 200 feet. Do you understand what's going on here? They've come around a turn, there's a straight section, and then there's a curve. So when you come around, not sure where that came from, and it won't erase. So when you come around this first turn, boom, here you are in this straightaway. Now in this straightaway, there's only 200 feet before you intersect or encounter the next turn. So you've only got 200 feet to get your car positioned, speed up, slow down, whatever it is you feel you need to do to get ready for that turn. And the question is, what is a safe speed through this area to ensure that you're not going to go off the road when you hit the curve up here? Make sense? Okay. Well, what we want to do is we want to look at, okay, speeds, got less than 200 feet, and solve that. And if you solve this, there are a couple ways to do this. One way is to do it graphically. And if you're going to do it graphically, you want to graph two different functions. You want to graph y1 equals 200. This would be in your calculator. Then you also want to put in this 1/12 x squared plus 11 over 5 x, and it's going to give you a parabola. If you want to know where this parabola is less than the 200, that's going to be this section right in here. Now, on this particular question, we could solve for where does it intersect here, and we could solve for where does it intersect there. However, does this value here make any sense? No, because it's negative, isn't it? And we're talking about velocities, like 40 miles an hour, 30 miles an hour, 50 miles an hour. Have you ever seen a speed limit negative 60 miles an hour? Not quite sure what that means. Okay, I guess you got to back down the road or something. Okay, but what you can do here is you can take a look at where is the portion of the parabola that we're working with below 200, and that would be this portion right in here. And you could come all the way over to this value here, ask it to compute it, and when it does, what it's going to display on the bottom of the calculator is x is 37.53. That would give you the maximum safe speed. 37 point, when was the last time you saw a speed limit? 37.536969 miles. Yeah. What would that probably be posted as? 35. Why don't they post it as 40? Round up a bit.
Too fast.
Too fast. Yeah, you'd rather have things on the safe side and have it a little bit too slow, because when people see those, are they going to really do that speed anyway? Probably not. So you want to set it down a little bit to keep them from winding up where they don't want to be. Okay. So what do you wind up doing when you're going to solve an inequality? It's actually pretty straightforward. Let's say we have something like this one, and we need to solve it. First thing we'd do would be to rewrite this as x squared plus x minus 2, moving everything over to the left side, like that. Does that make sense? Now that you have it all on the left side, see if you can factor this. Well, this one will factor in x plus 2 and x minus 1 greater than or equal to 0. Okay. What's that give you then for your x values? Yeah, a -2 and a +1. And this is where you set up that number line thing again. This time we're going to do our -2 and our +1. By having it factored, it makes it very easy to figure out if it's positive or negative. For example, we could choose -3 as one of our values. So if we plug that in there, we're going to have -3 plus 2 times -3 minus 1. Well, let's see, this is going to be a negative, that's going to be a negative, so it's going to wind up being positive. Did you notice that I didn't bother getting any numbers at all, did I? In the middle interval, what's an easy number in the middle to work with? 0. Plug in zeros, this is going to be positive, this is going to be negative. Aha, so the center section is negative. Whoa, Chuck, that was awful fast. Yeah, I intentionally did that fast, so trying to encourage it. You know what? Without messing with a bunch of numbers, you can figure out where this is headed, can't you? Which is kind of good news. Okay, let's do the rightmost interval. That's going to be something like over here. Let's pick 2. So I'll put in 2. 2 and 2 is positive. 2 minus 1 is positive. Aha, this will be positive. Now, you've got the different intervals set up, identified positive or negative. And now what you want to do is to, with this, decide, are we shopping for positives or are we shopping for negatives? We're shopping for positives this time. And can we actually use the endpoints of the intervals this time? Yeah, because it's equal, isn't it? Greater than equal. So what that's going to allow us to do is on this one interval, we can start at -infinity and go all the way over to -2. Are we allowed to include the -2? Yeah, so we can do a bracket, union with that, and we're going to start at 1 because we're allowed to include 1. And how far can we go there? To infinity. And there it is. This stuff is just that straightforward to do. Does this look familiar to you from somewhere in the past? Okay. They've set up a table. If you look through your book, they set up a table to do what we just did on this number line. Notice on the table it said positive, negative, positive. Well, that's what we've got going here on the table, or on this number line. The positive, negative, positive. Either way will work. Okay, that is good news because that finishes that out and gets us into chapter 4. All right. Where we're headed with chapter 4 is we are going into stuff beyond quadratics. Yahoo. Please? Yeah, finally done with the linears, done with the quadratics. The only place you can see them now is in the rear view mirror of the homework. Okay? What this is going to do is it's going to move us into scenarios where we're going to be looking at the functions and the graphs of those functions when the function is more complicated than a quadratic. Now, when the function is more complicated than a quadratic, you can still have an idea of what the graph looks like, depending on the function. You can still have an idea of how many solutions there are. Okay? But what we're going to wind up doing is we're first going to start out with a new way of writing a polynomial. You may or you may have never seen this notation before, and if you haven't, that's fine. The idea here is, do we really know what the high power of x is that we want to use? Do we know what our biggest exponent is going to be? Could change from one problem to another, couldn't it? So what we're going to do here, instead of writing down specific numbers, we're going to say, you know what? Whatever it is, our biggest power of x is going to be n. This could be the 89th power. Now, the next thing you have to be careful of is you see these coefficients. Are they all going to be the same from one term to the next, or are they going to be a mix-up batch of different numbers? They're going to be mixed up, aren't they? So what they wind up doing is they say, okay, a is going to be some number, but we're going to put this little subscript n so that it matches with that particular exponent. If this was then x to the 1 less, well, that'd be the 88th power. Then this would be a sub 88. And this allows you to go as far as you need to go then, doesn't it? There are two things that we can pull off of the first term. One of them is the leading coefficient. Okay, the leading coefficient is that value right there. You know, with a polynomial, or well, with a quadratic in particular, if it's negative, that means the parabola is opening down. If that leading coefficient is positive, it means the parabola is opening up. Okay, so you can get some information off of that leading coefficient. The other thing that we're going to look at is what's called the degree of the polynomial. The degree just means what's the highest power on the exponent. If we had 37 x to the 89th minus 25 x to the 45th plus 17x squared plus 3, the degree of the polynomial would be the highest power of x. So the degree of that polynomial would be what? 89. One of the ways that they will write the degree is they would say something like the degree of f equals 89. That degree is important. The degree tells you how many solutions you have. You know, like x equals 3, x equals negative 5. This would have how many different answers? 89. That'd be a lot to have to solve for, wouldn't it? Yeah, we'll use the function, yeah. Okay. Now, does that mean it will always have 89? No. Okay. Even if it says x to the 89th, it may simplify to something like it only has one solution. Really? Yeah. How about x to the 89th minus 1 equals 0? What value goes in there for x that'll work? What number can you raise to the 89th power, subtract 1, and get 0? 1. Yeah, it's the only number that works there, isn't it? So even though the degree is 89, it says it can have a maximum of 89 solutions, but in reality this just has 1. Okay? That's the maximum it could be, but it doesn't mean it has to have that many. All right, so what are they doing here? They're throwing some different polynomials at you. They're asking you to practice up on identifying the degree. Well, on this first one, this is really 10 times x to the 0 power, because anything to the 0 power is just 1, isn't it? So x to the 0 is just 1, so that's 10 times 1, which is 10. The degree is 0. So if it's a constant, the degree is 0. If it's a linear function, the exponent's a 1, so it has a degree of 1. How about this last one here? What's the degree of that puppy? You see it's going to be 6. And the leading coefficient, that's the coefficient on whatever the highest power of x is there, is a negative 1/2. Real fair question for Friday's quiz is to list, well gosh, what's the degree and the leading coefficient? Then also ask you what's the maximum number of solutions this could have. Doesn't guarantee it'll have it. You just saw one like that. Okay. But as soon as you have the degree, you know how many solutions are possible, don't you? So that part's easy. All right. Next thing, maxes and mins. These are important a lot of times because if you have a cost function equals some mess, do you want to maximize or minimize your costs? Usually you want to minimize them, don't you? So what you want to be able to do is to graph this thing and find the lowest cost. Well, the lowest cost would be right there, wouldn't it? On this first function, does it have a lowest cost? Yeah. On the first one, you got a lowest cost right there. On this second function here, you've got a low cost there, but is that as low as it goes? No. This is a local minimum. Local means compared to things around it, it's the low point. But global or absolute minimum, there is no absolute minimum because where does this graph stop? Going down. It doesn't, does it? So you can have a local minimum here. You won't get a global or absolute minimum. However, in the first one, the polynomial, does it have a global minimum? Does it have an absolute lowest point on it? Yep. It's right here. Make sense? Okay. A function can have several different maxes or mins. In this particular one, it has two maxima. They're both at the same height, aren't they? So the absolute maximum on this is 11. Now, does the maximum refer to the x or the y value? The y value. So, for example, if this was cost, what's the absolute maximum cost of this thing? 11. If this was profit, what's the best we can do in this scenario? Same thing, 11. It gives you the maximum. Does this function have a minimum? Well, let's see. It says that it has one absolute minimum. Okay. This point here is a minimum. These, realistically, okay, we talked about before, is going down to a minimum. But can you ever really get to where they're going? No. And if you can't arrive there, do you have an actual point? No. So do those actually yield a minimum? No. Okay. Are you okay with picking out the max at 11, the minimum at a little bit less than 3? sense? Or right around 3? All right. These are important as you move forward. You can have an absolute or global, either word. Absolute or an absolute maximum, a global maximum. What that means is this is the absolute highest the thing goes. So you could have a graph that goes like this. Does it have an absolute maximum? A place that's the absolute highest? Yeah. The absolute highest is right there. Now, an absolute maximum is different from a local maximum. Does Cincinnati have a highest hill? Yeah, Cincinnati does have a highest hill. Is that the highest place in the world? No. Locally, it's a high spot, but globally, over the entire globe, nah, it doesn't even come close to it. So something like this, that might be the highest hill in Cincinnati, would be a local maximum, but not a global maximum. This point right here would be a local minimum, and it would also be a global minimum. Okay, so let's take a look at some examples of what's going on with this. We've got this function. What on earth is this function? Well, what degree is this function? It's a 4th degree polynomial, isn't it? Total number of solutions possible? 4. Okay, what does this represent? It talks about the average ocean temperature by the month in Bermuda. Okay? Now, you need to notice here that 1 corresponds to what? January. 12 corresponds to December. Oh, okay, so X is just going to be the months of the year. And when you plug it in, okay, you're going to get different temperatures. Notice as well the domain of this. Why does this domain only go from 1 to 12? There's only 12 months in a year. And you can't go negative months, can you? The months are January to December, and that's it. Okay. What we could do is we could graph this, and you'd get something like this. On the calculator, you can go ahead and find the minimum. It'll look for a minimum for you if you, on the toolbar up at the top, if you select Calculate, C-A-L-C, it'll, when you go to a minimum point, it'll compute what that point is. But there are other ways to do this with Excel and all kinds of other stuff too, so it's not the end of the world one way or another. Wolfram Alpha is a good place to go. This point right here is a minimum. It's at 261. What's that tell you? Yep. In February, the temperature of the ocean is going to be around 61 degrees, which is as warm or as cold as it gets. That's as cold as it gets. If we were to go over to here, right along in there is the maximum, isn't it? Okay. If this is 2, what's this going to be about? A little over halfway, isn't it? So that might be around 7, around 8, something like that. Okay. So if you were going to Bermuda and you wanted to find the maximum temperature, the maximum is going to be at about 7.5. What does that mean months-wise? About halfway through July? Because we're not to August yet, are we? 7.5, 7.6 is not to August yet. So we're still in July, but we're about halfway through, a little over halfway through. So if you were to go like the third week in July, what would you expect the ocean temperature to be running? About 82 degrees. Does that make sense on how to use the mins and the maxes and all that good stuff on these? Okay. When we're dealing with these various polynomials, there are a couple things we're going to want to understand so we have a better or quicker idea of what the graph is going to look like. You can have functions that are even. Okay. An even function or even symmetry means that it is symmetric around the x-axis. Now, if I could take this screen, and I know maintenance doesn't want me doing this, but on this parabola, if I could take the screen and fold it along this y-axis, do you see that the two sides would fold up and be identical? On this bell-shaped thing, on the y-axis could fold it and two sides would match. On this one, this is a fourth degree polynomial. The two sides could fold them and it would match as well. If you can fold the graph in half on the y-axis, now this is important, it's got to be on the y-axis. If you can fold it in half on the y-axis, you have what is called an even function and it has even symmetry. There's a reason for it being called even. We'll get to that here in a few minutes. Okay. So you can see with each of these that you can fold them up. With each of these. With this one you can fold it up. Now, if the function is even, here's something real important. An even function means that if you plug in the negative, you'll get out the same results as if you plugged in the positive. Man, how could that be? Well, imagine something like this. Y equals x to the 16 minus x to the 10th plus x to the 4th plus x squared. All of the exponents are what type of values? They're all even, aren't they? So if I plug in 1, I would do 1 to the 16th minus 1 to the 10th plus 1 to the 4th plus 1 squared. That's going to give me the exact same result as if I took negative 1 minus negative 1 to the 10th plus negative 1 to the 4th plus negative 1 squared. Because if you raise negative 1 to even powers, it's always going to come out positive, isn't it? Which will be the same result as if you had plugged in positive numbers to begin with. Now, because the negative and the positive are going to give you the same result, that means they're going to give you the same y value. That means that the y value on the right-hand side of the graph is going to be the same as the y value on the left side, and that's what gives you these symmetric graphs. Because the y value over here matches the y value over here. The y value over here matches the y value over there. Okay? And that's what's going on with an even function. The other thing that you can wind up with is what is called odd symmetry. Now, with odd, imagine if we could take this first graph, put a nail through the origin, right in the center, and spin it 180 degrees. If we spin this 180 degrees, what's pointed down now will swing around and then it'll be pointed up, won't it? And what's pointed up will spin around and it'll be aimed down. So if you take it and you spin it 180 degrees, you get back the same thing you started with, don't you? That's kind of weird. That is referred to as odd symmetry. Okay, you ready for a rough guess here? What do you think all of the exponents on these polynomials are going to be? Odd. So if you have something like y equals x to the 7th plus x to the 5th minus x cubed, like that, something a little different is going to happen when we plug in our x values. If we plug in a 1, okay, it's going to give us something very different than if we plug in a negative 1. The very different that we're going to get is, in the second case, negative 1 raised to the 7th power is what? It's a negative, isn't it? Okay, so this is going to give us a negative 1. Negative 1 to the 5th power is a negative. Negative 1 cubed is a negative, but we're going to subtract it, so it's going to be plus. Now, originally, what we got back was 1 plus 1 minus 1. Now what we're getting back is minus 1 plus 1. Every single sign on the second one is what compared to the first one? They're all the opposite, aren't they? We could rewrite this second one, this, if we factor out a negative, it would be 1 plus 1 minus 1. Does that make sense? Okay, which is going to give us on the inside whatever it was we started with. So what this says is, if we, let's see, here we are. If we take the negative and we plug it in, where'd it go? Take the negative when we plug it in. It's the same thing as doing the negative of the other one, which is exactly what happened to us down here. Do you see this right here? The negative 1 out front is the negative of the original function. Okay? What that is the negative of the original function. So what it does is it takes all the y values and it swings around negative from what they would have been. Does that make sense to everybody? So you want to be careful. Even functions, odd functions. Know that there are two different types of symmetry. The graphs are going to be different. The one's going to be symmetric around the y-axis. This is going to be symmetric around the origin. That means you spin it 180 degrees. Okay? So there's the difference even in the odd functions. Hey, if you have a table, one last little blurb here. We'll call it quits with this. If you have a table, how can you tell if this is even or odd? Look at negative 3 and positive 3. Do the values come out the same or the negative of one of another? They come out the same, don't they? Look at negative 2, positive 2. They come out the same. Look at negative 1, positive 1. They come out the same. Would this be an even or an odd function? This would be even. Because it doesn't matter if you plug in the positive or negative, you get the same thing out. And the way for it to not matter if it's negative is for all the powers to be even powers. Are you good? Lots of definition-y stuff here today. Folks, I hope you have a terrific day. I look forward to seeing you all on Wednesday. Okay, and the homework's up. There's some more going to pop up. Plenty for you to fiddle with.